Hello students, in the last class we have studied three main definitions about the topology on the real line. Those were the standard topology on the real line, the lower limit topology on the real line, and the K topology on the real line. We have also defined the subbasis for a topology on X and topology generated by the subbasis, and we have studied some results based on them. Now in this class we are going to study some examples based on the topology. So let us begin. First example is, if family to alpha is a family of topologies on X, then show that intersection to alpha is a topology on X. Here it is given that we have family to alpha as a family of topologies on X. Means this is a collection of topologies on X which may be finite or infinite in number, and we have to show that their intersection means intersection to alpha is a topology on X. This same statement can also be stated in the different manner as the intersection of topologies on a set X is again a topology on X. We will solve this example. So solution of this example, which is also a proof. So solution, or it can also be called as a proof, is, so first of all it is given that X is a topological space. So let X be a topological space. Let X be a topological space and to alpha be a collection of topologies on X. Be a collection of topologies on set X. Then by definition each to alpha satisfies all three conditions. Satisfies all three conditions required for being a topology. We know the definition of the topology. If X is some set, then the collection of subsets of X will be called as a topology for X if it satisfies three conditions. The first condition was the empty set and the complete set X should be in that collection. The second condition was arbitrary union of any subcollection of elements of that collection should again be an element of that collection. And the third condition was intersection of finite number of members of that collection should again be a member of that collection. So likewise, as we have supposed that family to alpha is a collection of topologies on X, which means that each member of this family is a topology on X, and as each member of this family is a topology on X, which means that to alpha for each value of alpha is a topology on X, and therefore by definition each to alpha satisfies all three conditions required for being a topology. Now, to show that intersection to alpha is again a topology on X, we have to show that this intersection to alpha satisfies all three conditions required for being a topology. So we'll show this one by one. So we'll begin with the first condition. As each to alpha is a topology, as each to alpha is a topology on X, therefore phi is the empty set and the complete set X both belongs to each to alpha. As each to alpha is a topology, therefore the empty set phi and the complete set X both belongs to the each to alpha. Okay. Now what does this mean? So this implies that phi belongs to each to alpha, and as phi belongs to this each to alpha, this implies that phi also belongs to the intersection of to alpha. And again, as each to alpha contains X, this means that X belongs to each to alpha. Complete set X belongs to the each set to alpha, and again this implies that X belongs to the intersection of to alpha. In this way we have shown that the empty set phi and the complete set X both belongs to the intersection of to alpha. Hence the first condition is satisfied. Now we'll move to the second condition. Now we'll show that the second condition is also satisfied. So the second condition, let ui, where I belongs to some index set. Okay, let ui belongs to the intersection to alpha. Okay, let ui be the family of open sets in to alpha. Then we have to show that their union is again in to alpha. Now as this family ui belongs to the intersection to alpha, this implies that the family ui belongs to each to alpha. As this family ui belongs to the intersection to alpha, this means that the family ui belongs to each to alpha, and as each to alpha is a topology on X, and as each to alpha is a topology on X, as each to alpha is a topology on X, therefore for each alpha, the union of any subcollection of elements of to alpha is into alpha. This is by the second condition in the definition of the topology. Okay. And therefore union of ui, union of these sets ui over I, union of these sets ui over the I belongs to alpha for each value of alpha. For each alpha belongs to the index set for each alpha. And as this union of ui belongs to each to alpha, this implies that this union of ui over I, this union belongs to the intersection of to alpha, belongs to the intersection of to alpha. So see here what we have shown in this second condition. We have considered a family of elements of intersection of to alpha, and we have shown that their union is again a member of intersection of to alpha. This means that the union of any subcollection of elements of intersection to alpha is again an element of intersection to alpha, which shows that the second condition also holds. Now we'll move to the third condition. Let u1, u2 and continued up to un are finite number of elements of intersection to alpha. Suppose these are finite number of elements of intersection to alpha. Now if each u1, u2 up to un belongs to the intersection to alpha, this means that u1, u2 and so on up to un belongs to alpha for each value of alpha, for each alpha. So u1, u2 up to un, all of them belongs to each to alpha. Okay. Next, now as each to alpha is a topology on X, as each to alpha is a topology on X, therefore for each alpha finite intersections finite intersection of elements of to alpha is into alpha. Is into alpha, and therefore intersection of ui over I equal to 1 to n means the finite intersection. So intersection of ui over I equal to 1 to n belongs to the to alpha for each alpha. And if this intersection belongs to each to alpha, which obviously means that this intersection of ui over I equal to 1 to n belongs to the intersection of tau alpha. So see what we have shown in this third condition. We have considered finite number of elements from the intersection tau alpha, and we have shown that their intersection is again a member of intersection tau alpha, which means that intersection of finite number of elements from intersection tau alpha is again a member of intersection tau alpha. This shows that the third condition also holds. So therefore, third condition holds. So we have shown that all three conditions required for being a topology are satisfied by the set intersection of tau alpha, and hence this means that intersection of tau alpha is a topology on X. Hence we conclude that intersection tau alpha is a topology on X. So like such, we have shown that intersection of topologies on X is again a topology on X. This is the first example.